In the last class, we have discussed about the DC characteristics. In the DC characteristics, we might have seen the input bias current, input offset current, the bias voltage, and the thermal drift. So, these are the characteristics in the DC characteristics. We have discussed about how the bias current works to make the voltage to get 0 with the help of the input voltage to be 0. So, in this case it will affect the steady state response of the op amp. So, in case of this DC characteristics, that was the drawback in that it affects the steady state response of that operational amplifier. So, in this condition we go for that AC characteristics. In this AC characteristics we are going to see about the three terms. So, the major when we look into the AC characteristics, the frequency plays a major role. So, in this AC characteristics, we are going to discuss about three terms. The one thing is frequency response. Second one is frequency compensation. Third one is slew rate. Now first we are going to look into the frequency response. So in this frequency response, we are going to look into the steady state characteristics, right? So in this frequency response, ideally an open loop, a gain with maintains a 90 decibel. So in this condition, for a DC characteristics, the open loop gain will maintain the gain with 90 decibels. In practically, it will get decreased. Practically, an op amp will get decreased with 90 decibels. So it again, in this condition, we will mention the term decreasing in the sense it's a roll off. So every time it gets a roll off with minus 20 decibels with the starting decibel range. So here we have why this roll off gets occurred. So in this, the gain of that amplifier, operational amplifier, gets roll off every time. Why it gets roll off? The thing, we are going to introduce a capacitive component in your operational amplifier. So introducing an capacitive component, a capacitive component. So this physical characteristics of this capacitive component, so gets roll off every time. So every time when we use that capacitive components, it gets reduced to minus 20 decibels. So this is the one thing, it makes the gain to get reduced. So here we are going to draw a high frequency operational amplifier circuit, the high frequency small signal model of op amp. So this diagram we might have seen it earlier. So initially we have a voltage V2, here V1, with the resistance at the input side is Ri, and we have a small signal model with the voltage gain of AOL and the differential voltage. So in this we are going to add a resistive component and a capacitive component. So a RC component is introduced here, and this capacitive component to be grounded, and the voltage is taken across this capacitive component V0 is the output voltage. So here this is like an input resistance, it acts as your operational amplifier. The internal, the thing of this is your operational amplifier. This is the output resistance. So here this is internal op amp operational amplifier. Similarly, we draw an op amp like this. We will be connecting a inverting and the non-inverting terminal, the output voltage V1, V2, and we get an V0. This is like an open loop diagram. So we mentioned the gain of AOL is nothing but your AOL is the open loop gain, and this is the difference between the two voltages is nothing but your VD is the differential voltage. This is the diagram we have drawn like this in terms of your high frequency model. So in this condition we are going to find the open loop gain of this voltage. So in this open loop gain, so here we are going to define for every capacitive component, we are going to define with a corner frequency. So or which is nothing but your break frequency. Okay, so here for that open loop gain we can define that V0 is equal to, here we have an R0 component and your capacitive component. So we have to write the R0 and capacitive component including with your open loop gain. Your expression will be like minus J into Xc divided by R0 minus J Xc into AOL into Vd. So from this part alone we are going to calculate that open loop gain output voltage with the help of your open loop gain. So in this condition we have written the expression as V0 is equal to minus Jxc by R0 minus Jxc into AOL and the differential voltage. So now I am making this Vd voltage to that other side. So V0 by Vd is equal to minus Jxc divided by R0 minus Jxc into AOL. So in this condition, I am going to multiply with the J component factor. So here I am going to multiply the J component, so which implies minus J is J square Xc by R0 minus Jxc, R0 minus Jxc into J, right? We are going to multiply the denominator factor into J and we are going to multiply with the open loop voltage gain. So here it is like multiplication, don't confuse with the text. Here we know that the J square value is minus 1. So here again I am replacing that V0 by Vd. This instead of this J square factor I am going to replace it with minus 1. So here it is multiplied, so we can write generally it as Xc, and now we can multiply those factors R0 minus J square, so it becomes plus Xc into AOL. So again I am going to replace that capacitive reactance in terms of omega, so I am writing 1 by omega C. So this is the factor, make it a. So now I am going to substitute V0 by Vd is equal to 1 by omega C divided by J into R0 plus 1 by omega C into AOL. So in this condition I am going to take the entire factor, denominator as omega C, the numerator value is 1. Again I am taking the omega C, so I can write J into R0 omega C plus 1 into AOL. So now I can make that numerator to the denominator and it can cancel those omega C factor. So 1 by 1 plus J R0 omega C into AOL. This is the final expression for this omega naught V0 by Vd. So now I am going to replace that omega factor into the capacitive factor. So I can rate the frequency. So frequency F is equal to 1 by 2 pi R0 C. So this, how come this 2 pi C? Now you know that 2 pi F is the frequency. So I am keeping that F as such omega by 2 pi. Okay, right? So 2 pi F into R0 C. So I can write this expression as A is equal to, this is nothing but your voltage gain. So V0 by Vd is again a gain. So I can write this as A. Here I can make it as A, then only it would be get confused. So the output voltage divided by 1 plus J F by F1. Okay. So here you should know that concept. Here we are taking F1 is equal to, so you will be getting 2 pi, F is nothing but omega is equal to 2 pi F. The same thing concept, F1 is equal to 1 by 2 pi R0 C. So this F1 is nothing but your corner frequency. So why we are defining that corner frequency? This frequency will be calculating with the help of your values of R0 and C. So we can easily get the frequency F1 as the corner frequency. So in this or it may be defined with the 3 decibel cutoff frequency range. So this is the range for your op-amp signal. So in this condition, we are going to draw the two types of characteristics. One is magnitude characteristics, the other one is phase characteristics. Okay, so as usual we know that the magnitude characteristics have been calculated by taking that square root of that signal, and the phase characteristics is always calculated by the phi is equal to minus tan inverse of B by A. So here we should know which is A value and which is B value. Coming to that magnitude characteristics. So coming to that magnitude characteristics, so we have two values, x-axis and y-axis. So in this x-axis we deals with the frequency in terms of the logarithmic scale. So the other frequency in terms of a decibel. So here I am going to take that gain in terms of decibel. Gain in decibel. So initially we defined that the frequency f will be less than f1 value. So here we are going to discuss with the three values or whatever may be the capacitive components, addition of the capacitive components. So in that condition, so here we are going to define we have a frequency f1. F1 is your corner frequency, and the more greater than F1 we have some value of frequency. I have designed it as F2 frequency. So in this condition initially we have a 0 frequency. So in that 0 frequency range your gain will be maintained at 20 log AOL. That AOL is nothing but your open loop gain. So in this condition your value will be like 20 log of AOL is the open loop voltage gain. So in that condition it maintains a 90 decibels value. So in that next when we apply for the frequency, so here the first condition your F1 F value will be less than F1. Now you have to calculate the value of F1 by using the formula F1 is equal to 1 by 2 pi R0 C. Now you have to decide which is your frequency, corner frequency. Deciding that which is your corner frequency, then you have to make it as a frequency F1. So this is like similar center of the frequency. This is not center for all the cases. So now I have considered this as the center one. So if we are the frequency F1 corner frequency less than that, it will be maintained as the 20 log AOL, which is nothing but your 90 decibel ranges. Okay, in that condition when we reach the corner frequency with the help of a 3 decibel, okay, like this it will be reaching a 3 decibel range. So this condition, this distance we maintain with is a 3 decibel. Then when first condition, if it is less than this, the magnitude of that gain is A is equal to 20 log AOL. That's a open loop gain. Okay, magnitude of gain A. Then condition when your frequency F will be equal to F1. In that condition, this F1 we call it as a corner frequency. So corner frequency your gain will be 3 decibel down. So in that condition whatever may be the decibel is maintained. So when we reach that corner frequency it may decreases to the 3 decibel from that AOL value. So the third one F is greater than F1. So in this condition this region beyond that F1, if it goes further that corner frequency, in that condition the gain rolls off. So already I have mentioned, so the gain rolls off at every minus 20 decibels. The gain rolls off. So in this condition it may decreases to minus 20 decibel. So in that condition I have to draw a circuit. It reaches somewhere. So this will be like minus 20 decibel per decade. It may decreases. So every adding of that capacitive component, your gain gets roll off by minus 20 decibels per decade. So this is the magnitude characteristics, the expression for this magnitude characteristics. So this will be calculated with the help of this gain A. So this gain A is equal to AOL, that's the open loop gain, by 1 plus J F by FL. So here I am going to write the magnitude characteristics. So it will be like the squaring of that component. So here AOL and depends, and in your denominator it may take that 1 plus F by F1 the whole square. To make everything a positive value, we will be taking a magnitude. So in this, based on this concept, if you apply 0 voltage, what will be the maximum gain? So 1 plus 0. So what will be your AOL for the frequency is F is 0, your gain will be equal to that maximum AOL gain. That's the concept. Then when we substitute some value for your frequency, corner frequency and your frequency F, then it gets compensated and it reduces to 3 decibels. So when we increase the value of your F1, F by more than F1, in that condition your gain gets roll off by 20 decibels. So coming to that phase characteristics. So coming to that phase characteristics, we have studied the expression phi. Phi is equal to minus tan inverse of B by A. So here in the condition, the B by A is nothing but F by F1. So here again we are going to draw the phase characteristics with the phase angle phi in y-axis and your frequency that will be measured in the logarithmic scale. The very important, it will be measured in that logarithmic scale. So first at frequency F0, what will be the phi value? So you have to substitute F is equal to 0, then tan inverse of 0, what will be the answer? So you have to identify like that. For example, when you substitute your F is equal to F1, in that condition minus tan inverse of F1 by F1, you will be getting minus tan inverse of 1. In that condition, what will be the phi value? Then if F value will be greater than F1, then what will be the situation? Okay. So that it may be considered your F as infinite. So minus tan inverse of infinite. So first thing, you have to substitute your value as 0, then you have to substitute your value as 1, and the third thing you are substituting your value with infinite. So you have this tan inverse, you have to calculate what will be the value of tan inverse of 0, tan inverse of 1 and tan inverse of infinite. You have to draw a curve according to that. So in this again, when your frequency is 0 and your phase angle, it starts with 0 degree and in case of your frequency F1, this is your corner frequency, and when we vary that frequency more than F1, it may reaches to a frequency to that infinite. In that condition, how your phase angle will be. So now I am going to draw the curve. It may touches somewhere your frequency will be this is 90 degree and here it may be like 45 degree. So in this condition, so it's a 45 degree. So that the condition for phi is equal to 0. When it gets your phi value 0, by varying your frequency F as 0 condition, then phi value will be 45 degree, that is at the negative degree it's a 45 degree only when the condition F will be equal to F1. That condition phi will be is equal to minus 90. So here minus 90 degree when the condition F will be greater than F1, or I can write it F value will be less than F1 by considering the two frequencies F and F1, that is your normal frequency and the corner frequency. We can draw the phase characteristics. So here your f is greater than f1, so it will be around, it touches, that means your frequency value will be infinite. So in this condition there will be a 90-degree phase change only when we use a single capacitive component. If we use the capacitive components more, for example 2 capacitive components, it may be reflection with 180 degree. So a single capacitive component to be used. So here we can't say that zero frequency doesn't occur in the log scale, So practically we can define that the zero frequency can be mentioned as below 1 decade below corner frequency. So a zero frequency in practical term we can mention that a frequency 1 decade below corner frequency. Okay, whereas in that infinite we are not supposed to tell about that infinite situation and the zero. So in that case of that infinite situation we can say 1 decade above the corner frequency. So these things to be remembered when for that phase characteristics. So the formula to be mentioned are A is equal to the open loop gain by 1 plus f by f1, where f1 is the corner frequency. Here the phi is equal to tan inverse of f by f1. Using that we are going to substitute the frequency value and going to obtain the phase value in terms of the characteristic curve. So again we are going to discuss if we add more number of capacitive components in our circuit. So here the voltage function, the voltage transfer function, okay, here I have written shortly the voltage transfer function in the S domain. So yes, we all know that in S domain can be represented as j omega factor. So here first we start with the gain, the earlier formula. Again I am rewriting A is equal to the open loop gain by 1 plus j f by f1. Okay, so here we are going to replace AOL divided by 1 plus the j frequency factor or to be used in the omega factor. So omega by omega 1. So again I am going to make it as the arrangement of the factor AOL divided by omega 1 plus j omega divided by omega 1 will be moved to that numerator. So here I can make it as AOL into omega 1 by s plus j omega, right? The s plus omega 1, here the j omega is replaced with s factor. So this is the factor used here. So here now I am going to use, this is in the S domain. So now I am going to add more number of capacitive components, considering a capacitive components at 3 stages. So I am going to add the capacitive components at 3 stages. Initially we have 1 stage capacitor. So I have taken my value as AOL divided by 1 plus j f by f1. This is the one frequency parameter, and the other factor including when we use the capacitor factor, we are going to have a capacitor, another corner frequency factor is 1 plus j f by f2 and another factor f by f3. So this is the 3 stages of the capacitor to be used. So in this we are going to, again we are replacing that AOL into omega 1. I am just writing directly as such, omega 1, omega 2, omega 3 divided by s plus omega 1. Everything I have mentioned in the S domain part. So s plus omega 2 and s plus omega 3, right? So here I am going to draw a frequency curve, that is your magnitude characteristics. So a particular AOL divided by 1 plus j f by f1 I have mentioned as modulus of AOL divided by 1 plus root of 1 plus f by f1 the whole square. Similarly, here again an f is taken. This is your frequency scale, it's measured in logarithm, and the gain in decibel. Okay. So in this condition, again initially with the frequency with F, you have your only one corner frequency. It is decided with F1. So here I am going to draw a corner frequency concept. This up to this you have a 20 log AOL. That's the open loop gain, 20 log AOL. It will be drawn from this. It touches the corner frequency F1. By default, thus for an ideal, it will be like a straight one. For this practical thing, it will be like a short curve with the difference between these two is a 3 decibel. Okay. So in this, from this reaches a frequency F1. So next to this condition, it uses the another capacitive stage. As I already mentioned, every capacitive component, the gain gets roll off by 20 decibel. So in that condition, the gain gets roll off by 20%. Then again in that condition, again the gain gets roll off by 20%. Similarly, it gets roll on. So here in this condition, so this is your frequency F2 and this is your frequency F3. If it further continues, it gets roll off. So in this range, so I'll be writing the frequency with the gain. So in this we are getting the low frequency to 200 kilohertz. It maintains 90 decibel. So here from 0 frequency to here the frequency it be at 200 kilohertz. So I can make as this one as 100 kilohertz. Okay, assume that this F1 reaches 90 decibel. Then starting from 200 kilohertz to 2 megahertz. So your value gets roll off from 90 decibel to 70 decibel. So in that condition, this may be your 2 megahertz. So below that, before that it has 1 megahertz. Okay. So here every time here we have minus 20 decibel decay rolls off. Here minus 20 decibel decay. So in this minus 20 decibel decay, it may get 90 decibels. In this condition, it may rolls to 70 decibels. So again it gets minus 20. So by increasing the more number of the capacitive components in our op-amp circuit, so every time it gets roll off to 20 degrees centigrade. Now as frequency is adding, the cascading effect of this RC comes into an effect. So here the rolling rate gets increases. Okay. So next topic is how we are going to compensate this with the AC characteristics. So the next topic is frequency compensation. The frequency compensation, so here as if we have studied in the DC characteristics, we have some compensation techniques to be included to make that output voltage to be 0 with the help of that input voltage. So here we are going to make that frequency to be compensated. So here one requires this frequency compensation technique. So one requires a larger bandwidth. So here we know that the bandwidth is the difference between the upper cutoff and the lower cutoff frequencies. So that range of that value should be higher, and by making the lower closed loop gain value, and it lowers the closed loop gain value. So far we have discussed in this concept as with the help of that open loop gain. Here we are going to introduce a closed loop gain. So in this frequency compensation technique is classified into two types. One is external frequency compensation and internal frequency compensation. So as we understood that the name itself, we are going to add some frequency compensation external towards the op-amp amplifier. In this internal, it defines an inbuilt frequency compensation in the op-amp amplifier. Okay. So in this first we are going to discuss about the external frequency amplifier. So the ultimate aim of this frequency compensation technique to make that larger bandwidth by lowering the closed loop voltage gain. The same concept is applied to that external frequency compensation. So here we are going to make a low closed loop gain. So for that we have focused on the two techniques. One is dominant pole compensation, and pole zero compensation. So here we used to say that numerator value and the denominator value. That numerator value we call it as zeros and the denominator value we call it as poles. So here we are going to make that dominant pole. So the pole compensation to be the most dominant. So here everything we are going to discuss in terms of that frequency parameter. So next comes is the pole zero compensation. So whatever we have studied in that frequency response, so we are going to analyze the frequency components, how that gain gets decreased by adding that capacitive component. So how it may be gets compensated. So in this first we are going to look into the dominant pole compensation. So in this dominant pole compensation technique, we have an operational amplifier A with a gain A. That input voltage we have applied is Vi, and we are connecting and resistive component and the capacitive component, and further at the end we are going to take that output voltage V0. So here whatever we discussed in that frequency response, that amplifier I have just made it with a symbol and inside I made it as a gain. Just this A represents these factors to be included in this operational amplifier, it is understood, and I am applying that input voltage Vi. So here that Vi voltage is applied, and we are making this uncompensated operational amplifier to get compensated. So here that uncompensated transfer function gain of this op amp is A, which is to be compensated with the help of this gain with the notation as A dash. So now we are going to make the compensation technique by adding a series of resistance and capacitance. So here that frequency value to be calculated with Fd, this is take it as the dominant frequency 1 by 2 pi RC. This is the frequency taken 1 by 2 pi RC. So here we are going to place an RC network in series with this op amp circuit. So here I am going to write the gain for this compensated network A dash. So as such the A represents the gain. Gain is nothing but your output voltage divided by the input voltage. So I can write the expression A dash is equal to V0 by Vi. So in this condition I am going to make that V0 by Vi in terms of that uncompensated transfer function. So again I am going to start, you have to remember all those factors. This A is equal to the open loop voltage gain divided by 1 plus J F by F1. So earlier the stage we have the resistor and the capacitive component. So I have to make the resistor and capacitive component to be like A dash is equal to your A into minus J into Xc divided by R minus JXc. So again I have to multiply with the J factor, and again I have to replace with omega factor and then with the frequency factor. So I can directly write my answer as A by 1 plus J F by Fd. So here I have already mentioned my Fd is nothing but 1 by 2 pi RC in this dominant pole compensation technique. So here the uncompensated transfer function of that open loop gain, is multiplied with this frequency factor, which gives the compensated transfer function A dash. So your A dash is nothing but AOL. Here it is the open loop gain. So it is mentioned as AOL by 1 plus J F by FD. Now we are going to add the upcoming stages of your RC network. So in that condition, we are going to write that A dash is equal to, so here the numerator we have an open loop voltage gain 1 plus J F by FD. So here we are going to add again 3 more stages of your capacitive. Then we can define F by F1, 1 plus J F by F2, and 1 plus F by F3. So in this we have, it keeps on going where this FD frequency will be lesser than F1 and the F1 frequency will be less than F2 and F2 frequency will be. Similarly, we can write the frequency omega 1 will be less than omega 2 and less than omega 3. Like that we can write for omega d. So I have written in the frequency term, so FD will be less than F1, F2. So again I am going to draw the magnitude characteristics with the frequency using that log scale, and for that y-axis it will be in a gain. So here that compensated gain to be taken into an account. So here in case of this frequency response, I draw the first circuit as such. So initially it cuts with the 90 decibel. So the frequency, it may decrease to 3 decibel. I have explained it already. So next, for every frequency it gets roll off capacitive frequency, it gets roll off to 20. So now I can make this as my F2, this as my F3. So here you can have some frequencies. So every time we have minus 20 decibel per decade, 20 decibels per. So this starts with 20 log of AOL, it's the open loop gain factor. So in this we have introduced an RC component, that too with the frequency response curve. So this curve alone has a frequency component RC network. Then we have added an RC network for further 3 stages. You have these 3 frequencies. So now we are going to calculate the values for 1 by 2 pi FC. So we are going to draw this frequency. So here I have named this term as the frequency dominant frequency. Okay. So in this we will be making that frequency FD value to be removed. Made it as the cutoff frequency in this here part. So this FD frequency will be passing to that F1 frequency. Sorry, it should come here. So without going to that 90 decibel and 3 decibel values, it slightly cuts from that 90 to the F1 value. So here that F1, then it doesn't passes to that F2 and F3 value. It results to that minus 20 decibels. So it directly stretches. So this part we call it as the dominant frequency FT condition. Okay. So the disadvantages of this compensating network reduces the bandwidth. So our ultimate aim is to increase the bandwidth by lowering the voltage gain. So it should be a larger bandwidth, but in terms of this dominant pole compensation, we have got as the frequency with lesser bandwidth. So in that condition, so we go for a pole zero compensation technique. So here in that pole zero compensation, we are introducing the poles and zeros. Again we are going to have an amplifier circuit, operational amplifier with a gain A. This will be the uncompensated function, transfer function. So initially we have an input voltage and the output voltage V0. So later we are going to add both zeros and poles. So here we are going to add a series of resistance and the output V0 is taken, and here we are going to connect the resistive component and the capacitive component. So here the resistive component R1, R2 and C2. So that the zeros. So here I am making it as representation as Z1, here the representation as Z2. So in this condition I am going to make, assuming my Z1 value as R1 and Z2 value as R2 plus 1 by j omega C2. So it is represented in both of the capacitive reactance factor. So here instead of that I can write JXC C2. Okay. So here next we are going to use that frequency parameter as 1 by F1 as 1 by 2 pi R2 C2. The another factor frequency is F0 is equal to 1 by 2 pi of R1 plus R2 into C2. So we have two frequency components. So now we are going to calculate that gain factor. So again this is an uncompensated. To make this compensation technique to get compensated one, so we are introducing the poles and zeros. So a series resistance R1 and R2 C2 to be connected. This is considered as the Z1 and Z2 parameters. So now we are going to calculate the gain of that. So here the gain will be calculated by using the formula A dash is equal to V0 by Vi. So initially this V0 by Vi can't be come across with this. So we have taking that parameter called V2. So here the voltage comes as V2, sorry. So I can write V0 and V2. So intermediate we have V2 at this. So I can write it V2 by V. Okay. So this V0 by V2 part we have the resistive RC network, and V2 by V1 as such the previous gain what we have written in this. So here I am going to make that a compensated gain A dash is equal to, I will be writing that final content AOL into 1 plus F by F0. This is the frequency to be added, 1 plus J F by F1 and 1 plus J F by F2, and one more term to be multiplied as 1 plus J F by F3 into, we have to multiply with that. So this factor alone, I can say it as V2 by Vi. So now I have to write with V0 by V2. So in that condition V0 by V2 I can write the expression as multiplying with that term. So 1 plus J F by F1, 1 plus J F by F0. So only I got that factor. Remove this factor, it will be like this. This is like a F1, F2, F3 factor. We are going to multiply with this one. So here I am going to mention my R1 value will be like more than or equal to 1. So again R1 plus R2, this R2 value will be equal to 1. Okay. So this is nothing but here 1 and 1. So in that condition you can make your F by F1 value and F by F1 to get cancelled. So I can write directly A dash is equal to AOL divided by, now you can include that F0 factor. So F by F0 factor and 1 plus J F by F2, we made cancel that F1 factor. So 1 plus J F by F3. Okay. So in this condition again we are going to draw that magnitude characteristics for this. So again the frequency sharp measured in the log scale and your gain in decibel. Okay. So again I am going to draw that. This is your F2, this is your F3, and this is your first corner frequency F1. So this is your 90 decibel initially we have, then agree 20 decibel per decade gets roll off minus 20, the same thing to be repeated. So this is the thing with no compensation. So here we have not added any compensation technique in this circuit. When compared, this is nothing but, this is similar to that, this is a no compensation, and here it's a dominant pole compensation. So this curve starts from this FD to F1. It's the dominant pole compensation technique. So in this we are going to identify your F0. So here we have an frequency factor F0. So here F0 factor is equal to 1 by 2 pi R1 plus R2 into C2. So here we have that F0 term that will not pass through that F1 frequency, it directly pass through that F2 frequency. So this is the 90 decibel frequency and it directly touches your F2 frequency. So in case this is your pole zero compensation technique. So here for this 1 by F1 and 1 by F1 gets cancelled. So now this is the pole zero compensation technique, whereas in case of your dominant pole, so now I am going to compare both dominant pole and the pole zero compensation. So I will be making here this F1 that may be passing to that F1 frequency. So it is your dominant pole frequency. So this curve dominant pole characteristics. So in this, the pole zero compensation may have a larger bandwidth, which results in the larger bandwidth, whereas the closed loop gain gets lowered. So here the next topic is internal frequency compensation. So in that internal frequency compensation, we have mentioned that we have to use that capacitor. It should be an inbuilt one. So when at what frequency that capacitor will get current will get shuts off. So we have to choose the capacitor value with 30 picofarad. So here we are going to draw a frequency curve. So again a frequency response, your x-axis in frequency and your y-axis in terms of the voltage gain. So earlier it maintained some decibels gain and it finally shuts off to that ground signal. That is your frequency with higher frequency with zero gain. So in this condition, when we use that capacitor with 30 picofarad, it shuts off that signal. So this is the frequency to be used in built of your operational amplifier. Coming to that last topic called slew rate. So slew rate is nothing but it is defined as the maximum rate of change of output voltage. So I'll be mentioning it here. Slew rate. So it is defined as the maximum rate of change of output voltage caused by a step input change, and it is measured in volt per microseconds. Initially, for example, consider this as your operational amplifier. A voltage circuit is given, the output. So this is a normal voltage follower circuit. So in that we will be giving your signal, input signal as Vm sin omega t, and your output follower, voltage follower, as I already mentioned, V0 is equal to Vi. So here that V0 is equal to Vi sin omega t. So in that condition, when we define that slew rate, it will be taken a small change, maximum change with respect to time period. So I can differentiate that Vm sin omega t is equal to Vm sin omega t and be taken as cos omega t, and omega t is omega. So I can mention Vm omega into cos omega t. So we are making that cos omega t value as 1. Then we can calculate that output voltage with Vm, 2Vm. This omega can be replaced as Vm into omega, or else 2 pi f into Vm. That's the concept behind that slew rate. So a maximum rate of change of output voltage to the step input volt, and it's usually measured in volt per microsecond.